Oh, dear Sebastian, thanks for being with us, and the floor is yours.
Okay, yeah, thanks for the introduction. I'm quite happy to be here. I hope, that you will be likewise entertained and informed after this talk. As has been proclaimed already, I'm talking about the path towards actionable XAI. I'm currently the head of the explainability group at Fraunhofer Heinrich-Hertz-Institute in Berlin, and I'm working in the field of explainability for close to 10 years now. And during the time, I have co-developed a lot of methods for explaining neural networks. And today's talk will be about, first, a little bit of intro on machine learning and AI, why we might need explainability. Then we go towards local explainability, which means per sample explanations, how they can be applied to achieve actionability in this respect, how they are limited, and then we are going to move towards a recent set of methods we have published on arXiv a couple of months ago, which are called concept relevance propagation and relevance maximization, which should bring explainability as a field to the next level. So AI, I think most of us, or I guess assume all of us, are familiar with the spectrum of possibilities of AI quality. We have methods which are able to do high quality text synthesis. We have seen methods which are able to predict the folding of protein structures, which is a quite complex problem, which was deemed to be unsolvable until very few years ago. And on the other end of the spectrum, we have really suboptimal behavior of machine learning models and AI models. For example, mistaking trucks in traffic for traffic signs and then causing an accident, or predicting medical risks based on non-medical or artifactual features. Most AI, or AI in general, is a very data-driven approach, which means if the artificial intelligence, side note here, I'm using machine learning and AI synonymously in this talk because AI is just so much easier to pronounce if you do it often. So most of AI is data-driven, which means if the machine or the model which comes out in the end is erroneous, it is suboptimal, it doesn't work perfectly, it's usually caused by the data representing the problem the model should learn, also is not fully representative and problematic in some way. And this means that we often have some problems in the data we are not aware of, and we cannot assume that all data sets are, I do it here somehow, that all data sets we're dealing with are flawless, or that there is any data set which is flawless. Common causes which have been discovered in literature are, for example, unwanted correlations in data, which can be picked up by the model, which we see to the left here. Those are examples for class both from the Pascal VOC datasets, former image recognition challenge datasets used for close to a decade. And in the right, we see labeling errors discovered by Stock et al. In 2018 in the ImageNet dataset, which, for one, limit the model's capability to really solve the problem, because labeling here in this case is ambiguous. And on the other hand, it prevents us from really assessing the quality of the model predictions, because for example, if the model would say this is a lemon in this case, it would be right, but we would estimate it based on our expectation of class label orange. So there's a certain imperfection in the data sets we're usually dealing with. So why don't we just avoid those issues by handcrafting systems which operate optimally and just do what we expect? For one, this would most likely fail due to the complexity we're currently solving with machine learning and AI. And on the other hand, this would stand in contrast to what AI is actually being designed for, which means automatically and algorithmically finding well-fit solutions to problems which are really hard to express by manually programming rules. For example, how do you measure the cuteness of a cat, for example? I would say it's pretty much impossible to achieve this without any machine learning help. Often this means that we end up with some black box models where we have a well-operating model which is known to achieve high accuracy values when tested on some test holdout data sets. However, we usually don't have an idea what's going on inside the box and what the rules are. The machine learning models, especially highly complex deep neural networks with millions of parameters, what they have learned during training and what strategies they follow in order to make predictions. We just have the answer. But in the recent years, the field of explainable AI has, okay, I'm already too fast, has made a lot of progress in order to answer partially the questions what the model is predicting on when it's seeing those examples. For example, does it use the boat in the leftmost image, left top image, to predict the class boat? Or if it recognizes the horses in the remaining 3 images, why does it recognize horses? And this is especially in the image domain where we deal with benchmark data sets, like it is often done in, let's say, fundamental research like I'm involved in. This is not that critical, but if you move towards highly risky scenarios like the medical domains where you have to rely on your medical AI expert systems in order to pre-screen in a correct way, or if you talk about autonomous driving or any other scenarios where health, money, and basically people's lives are at stake, we don't want to fly black box models blindly. We want to have a glimpse into the insides of the black box machine, and we want to know what's actually going on in order to verify predictions or have tools or at least an outlook for fixing what's going on. Like I've already teased, local explainability has made a lot of progress in the last decade with countless approaches having appeared in literature. Local XAI can be summarized as tools of explainable machine learning, which for each prediction a model makes, allow us to get an explanation, mostly in terms of a heat map, which can be aligned to the input image, like you see to the left here. And there are different ways to come up with these explanations or interpretable feedback, like I actually should say, because this is what it is. Because in the end, we have to look at the heat map, and then we have to interpret what's going on in the image and what the model might have been used. So the text you see below this black box basically is my interpretation of what the model has been using based on the image I have fed onto the data, the model, and the heat map, which is the result of an explainer applied to this whole prediction process. In order to briefly summarize how explainability works, and with a focus on relevance propagation, this is a method we developed between TU Berlin and Fraunhofer HHI and published it in 2015. I'm focusing on this one right now, but in principle, the outcome is comparable between many methods. So let's assume we have a deep neural network model which has been trained to predict the gender of a person's face based on an image input. The possible outputs are male and female. Also, we have output neurons for male and female. And what we do is we typically take an image and its pixel values, we feed it into a neural network input layer where each voxel, which means subpixel, pixel location, and color value, is provided as a numerical input to the network. And the network then reads, in air quotes, this information by performing weighted transformations of this input data. And these transformations then move the representation we have in the beginning in input space through the model. The network does something with this data. It extracts features and so on. Features are recombined, re-extracted layer by layer. Usually the abstraction level of the representations in latent space, so in this hidden space, they increase until at the output we get an outcome representing the abstract concept of gender, for example, here male and female. What LRP does as a decomposition-based method, or a modified backpropagation-based method, it, in a nutshell, it follows the forward transformations made by the model, which it has done or did in order to arrive at the prediction female in opposite direction by allocating relevance scores to latent neurons. And in a nutshell, it works like this. Let's say we have any neuron, it fulfills some task, for example, recognizing eyebrows and so on. And this eyebrow recognizing neuron receives a relevance score, which reflects how useful and impactful it has been during prediction. This score for this neuron, let's pick this one, for example, is then transported back towards its input neurons based on how those neurons contributed to the activation or recognition of the eyebrow. And the relevance score we backpropagate usually is, in first instance, network output, because we want to explain what the model predicted. And it represents the usefulness of certain bits of information. And if we do this until the input space, we have marked all the network components according to relevance. And we see an input space an interpretable heat map, which tells us in red color which features or factors in input space, in this context pixels, or hot colors, not just red, basically red to yellow, have contributed positively to the recognition of this female gender in this case. And the blue ones tell us which factors in input space, which pixel values or image regions contradicted the made prediction and the explained prediction of female. Black color here means, and those are input regions which did not have an impact on the prediction in this case. And we can read from that that the hair basically is the indicator for the female gender, which has been recognized by the model. However, the mouth and beard area, they contradict the prediction for the female gender. And with this, we have tools to interpret and understand parts of the reasoning of what deep neural networks are doing, or this particular deep neural network has been doing with this particular input image. So if we go back to the examples shown earlier with the horses and the boat, we can apply this layer-based relevance propagation technique, and we see via the heat map here, this is a different color scheme where green is the actual neutral color, blue is again negative, and yellow to red is the positive color space. We see that in all those examples, why the predictions have been correct and a boat has been recognized and horses have been recognized, the reason for this recognition is completely object unspecific. For example, the model predicts that there's a boat in the image because the bottom third of the image, there's water. Or it recognizes the horse mostly based on the hurdles, the horse is jumping over. And which is usually, if you want to deploy machine learning models in avoid. Am I dropping out right now? I get a warning that I'm unstable. Can I get some feedback?
You are unstable.
Okay.
Let's continue.
Okay, let's continue. All right, but in this case, the results are pretty obvious, which means the features used by the model are well located, they are locally constrained, and there's no confusion about what the feature could be, which has been recognized here by the model and used by the model for prediction making. So this is a first step towards actionability, which means doing something with the feedback we have at hand here in order to fix the data sources, for example, or apply some transformations on the data in order to focus the model on the actual objective of the task. So this leads me to the step of defining actionability. So in a nutshell, I've already teased it. Actionability or actionable AI means that we can get feedback from explainable AI algorithms, which are empowering us as users or developers or stakeholders in any case, in order to do something with it, which means using this information in order to improve models, data sources, or so on, or as an end user, for example, use this information in order to review an automated AI-based decision. For example, if it would concern my person, if I would apply for a credit, financial credit, and I wouldn't get it because some AI says, no, you don't get it. I would like to know, why is it the case? Is it because of my, I don't know, background, or is it a valid decision, or is it some biased decision, and so on? And there's a recent paper from Hacker et al. From this year titled Varieties of AI Explanations Under the Law, which perspective. And what they do is they create those two axes of analysis: goal orientation of XAI and cognitive optimization of XAI. And from my perspective, from my experience, most XAI applications and methods are in the left corner. There's very little cognitive optimization, which means in this case how processed is this information And presentable is this information for the layman in order to understand what the model is actually doing, with the goal of minimizing the interpretation gap, which will make the problem of interpreting explanations as we see it in heat map level quite clear. Most of the stuff will be to the left, and there's currently ample movement towards the vertical axis for the goal orientation bit, and which means they're doing something which XAI feedback, which doesn't require any cognitive workload in order to understand what's going on, but we can use it outright, and there will be some examples in a second also. The European Union is basically has published the GDPR in 2018 and the AI Act, I think this or last year, I get confused. And both are basically targeted at two different corners of the spectrum, where the AI Act is more compliance oriented and targeting professional operators which work with AI. The GDPR tries to protect end user rights, for example. And this is where also the big gap is, this gap of understanding what's actually going on without much training. But in actionable, explainable AI in literature, some of the works from our group, for example, they use feedback for increasing model efficiency or avoiding catastrophic forgetting. So if you remember from a few slides back, I've shown how a label's relevance propagation works and how we propagate this relevance quantity through all the network in order to flag the network parts for their impact on decision making. And for example, we can use this information under the assumption that typically neural networks or deep neural networks with millions of parameters are highly over-parameterized. There's also ample literature on that discussing the ideas of neural network pruning. This train of work actually started in the 1980s and 1990s already. But in recent years, more efficient methods have been proposed, and one of our methods is actually based on explainability. And if you use, for example, layer-based relevance propagation and have flagged the parts of the network which on a handful of reference samples, usually 5 to 10 per class, are involved in solving the task, we can iteratively start removing those parts of the network which have a low relevance score, which means those parts of the network which don't do anything. And with this, we were able to achieve actually quite stunning results by being able to remove way above 90% of typical test performance, like you see at the bottom left here. And this can also be used, for example, to achieve domain adaptation, which means we can start with one network from one domain, which has, for example, been trained on ImageNet, and I want to transform this network to be able to solve my particular personal dog versus cats photo recognition task when I have a lot of images from my pets. I can use this to move this model, which has been pre-trained without much effort, to my particular, by just kicking out everything which isn't needed. Another work which has been published this year by AIDA et al. Is concerned with avoiding catastrophic forgetting. So catastrophic forgetting is basically an effect in neural network training, which happens if you fine-tune a network, during which the network shifts its parameter space to best fit the most recently seen samples, which means if you have your model pre-trained on some task A, and afterwards you train task B, the model will very quickly forget how to solve task A, and in the end only be able to solve task B. We use basically the same idea of flagging neural network parts which are useful for solving task A, and then we reduce the learning elasticity of those parts to a bare minimum, or even set it to 0, to only concentrate further training to the still useless parts of the network which have not been actively used in part A. And with that, we are able to train neural networks with limited data sources iteratively over many tasks, and in the end they are able to solve all the tasks which they have seen in the past already without forgetting anything. Both of those approaches, I would say, are again more to the left of the spectrum. They are not cognitively optimized, and they are purely goal oriented, which means we compute those attribution scores with our XAI method, which flags neural network elements. And this is totally enough to run those algorithms. We do not need to understand what the model is doing, but we still use XAI feedback in order to achieve those goals. Other recent work in the domain of basically using XAI to improve things or understand things are, for example, meta-analysis of attribution data. To the left, for example, there's a scatter plot of a result achieved with spectral relevance analysis, which uses thousands of heat maps computed by an explainer on top of a model for those thousands of samples, in order to find systematic patterns and strategies used by the model, which repeat in the data or repeat in the decision-making of the model over a test or training set, for example. And this can be done in input space, in pixel space, or in any latent space. So the idea here is to achieve cognitive optimization by doing data processing on explainability. And this will, in a later slide, actually the next one, help us to improve models again. The right example takes place in epidemiology, where we are also moving a bit towards the cognitively optimized space of XAI, however, not due to the explanations themselves, but due to the use of a purpose-built model, which is built in order to positively combine medical features of patients, for example, what's the gender, drug use, yes, no, does the person smoke, and so on. Basically, features describing the medical record of a person. Those are combined in a latent space, and the task of the model is then to figure out what are the causes, to figure out the task of using this medical information with a pre-built or constrained, so to speak, representation space in order to solve the task of risk prediction for particular diseases, for example. Here in this case, we can then, since it's a purpose-built model and we know how it roughly operates by only positively combining features, for example, again, use explainability in order to execute a knowledge discovery task by finding out if you have a disease A, for example, what are the actual causes which are indicative for disease A? And this can then be used to further understand the data domain and get new insight about how this particular disease we have now analyzed, or the model has analyzed, expresses itself in order to increase the speed of disease recognition and taking countermeasures and so on. Finally, there are a bunch of works which directly target fixing model behavior or constraining model behavior during training. And they are during the 2017 to 2020, there's a bunch of methods which works with adding a secondary loss to the model training, which works with explainability feedback in order to improve the model behavior. So in a nutshell, those methods basically, they train a discriminatory task. So try to align the prediction of the model with a target class or object label, but at the same time, they try to come up with a desired explanation. And they do this, for example, in an iterative, interactive way, where experts are tasked, does the model behave in this case in the correct way? And the expert can then potentially provide a ground truth heat map, which means marking the area the model should look at in terms of image recognition in order to solve the task. And usually in this case, this works well if the data can be, or the data can be well annotated. For example, if the concepts are clear, for example, this is a building and the rest of the image are non-buildings. But it might be difficult if you, for example, have, I don't know, random art and we classify sentiments associated with those art pieces. This might become difficult in this case. So here, cognitive optimization is not really present. This is mostly goal-oriented and only works if cognitive optimization or optimized data is somehow present already. One work from our group uses the spectral relevance analysis, the cognitive optimization achieved by spectral relevance analysis in order to fix model behavior by finding, for one, characteristic behaviors, which are then presented to humans in terms of example images, which fall in this behavioral cluster with heat maps as added information in order to understand how the model is actually acting in this cluster. And this information then can be used to actually model countermeasures or compensatory steps for further neural network training or for outright suppressing undesired features. And I would say this is a two-step approach because we rely on the increased cognitive optimization of the explanations in order to take causal and countermeasures, or in the first instance to really understand if this particular behavior by the model is desired or if it should be removed at all costs or at any cost. And modeling can then take place, for example, by training again a model for a malicious concept, for example, which can then be injected into the model, the task solving model, in order to remove some certain influence and, for example, get rid of this copyright tag of this horse image, or get rid of the sensitivity of the model to the copyright tag of the horse image. There's also a paper from 2022 from Leander Weber et al., which provides an overview over the current developments in XAI-based model improvement, which target different aspects from data to loss functions and so on. Okay, so what about local XAI and cognitive optimization? I said before that, also in the previous slide, that there are some approaches using local explanations in order to, there are some pluses actually here missing. There should be pluses and there should be an equal sign. There are some approaches which use local explanations as feedback in order to achieve some goals. Half of those methods are not cognitively optimized. They don't need to, or stakeholders do not need to understand what the model is actually doing in order to use this information in order to achieve some goals. And a few methods are trying to achieve cognitive optimization by doing data processing on large amounts of explanations. When we compute local explanations in the first hand, what we usually do is we pick one output of the model, for example, the prediction the model has made, or just any output we're interested by. For example, has this 8 not been predicted as a 3, and then we can explain the case 3. In this case, we get an explanation which marks parts of the 3 in red color, which corresponds to 3ness in this case. And those parts are blue because they speak against 3. So we have a context which is provided by picking a particular output of the network. And this allows us to make an interpretation in the first place. For example, would we try to explain all the outputs at once, we would kind of get this map of somehow importance, which has no particular meaning, and we wouldn't be any further than we were before. However, there are problems in solved by machine learning models, which are still roadblocked in this sense. For example, here we have a bird classification task. We again compute heat maps for the predicted class, and basically every heat map targets the bird's face and parts of the body, which means we are not very smart, much smarter than before. We know that the model is dominantly using bird information in order to make the assessment, but every explanation basically looks like this. This is a sooty albatross, for example, because look at the whole bird, there it is. So there's no information gained in this context. The problem, why this persists, applies to all backpropagation-based explainers, but also in general to surrogate models like Lime, Shep, occlusion, and so on. And those methods, they either compute explanation scores which travel through the network and arrive in input space, or they are outright generated in input space. And they have in common that this information, the explanation information, is basically a superposition of influences representing the inner workings of the neural network. For example, let's assume that the network has learned detectors for particular beak shapes of a bird or a particular type of plumage and featherwork. If we follow those tracks of relevance, in this case, traveling through the network, they will coincide at some point, for example, in similar image areas, or for example, the beak type feature could be extracted from the same image area of like the plumage type, because the plumage type covers parts of the bird's head. And this leads to a superposition which mashes up all those influences of the model's decision-making in a single heat map in input space, which means for us as researchers and users who want to interpret this feedback that we are basically losing access to a lot of this information which is available in explanations. And the next generation of explainability is currently trying to solve this, or working towards solving this, by combining local explanations and global explanations at the same time. Local, we have already discussed. Global, in a quick summary, is basically tries to communicate what the meaning of those learned encodings are by mostly providing examples and so on. There's a prominent paper from Cynthia Rodin's group, ProtoPNet, which is using purpose-built models again, which have reserved representations for concepts which are human interpretable in order to achieve this goal. But in this work, I'm going to focus on our latest method or set of latest methods, which are called concept relevance propagation and relevance maximization. And there are some objectively good reasons to do that. And for example, our method is completely post hoc, which means we don't have any requirements during training. We don't need extra data. We don't need extra data model architectures. You can just take your model, plug it in, and then you can obtain local global explanations, and this quite efficiently and quite fast. And the goal with this is, in the first instance, to increase the cognitive optimization of the explanations by providing human understandable feedback in terms of not only partial heat maps, which represent parts of the decision-making of the model, but also to supplement this with examples of what the model is actually seeing. For example, all those explanations for different age predictions, they use the eyes, but the eyes in all of those predictions are completely different, right? Young children's eyes versus wrinkled old guy's eyes. And this information, for example, would be lost in a superposition in the heat map alone. And this should act as a stepping stone for novel tools for using explanation in actionable and at least human interactive kind of actionable way. Okay, now I'm going through basically both methods we have, or both concepts we have proposed, and we start with the concept relevance propagation. The basic idea is, or let's make for now, let's make some assumptions that certain transformations or layers and channels in those layers are used by the model to encode code-specific information. And the next assumption is that we know what those meanings are. Usually we don't know it, but that's not bad because this whole process can be fully automated, and this knowledge will come with the relevance maximization step. What concept relevance propagation basically does, it extends the toolset of layer-wise relevance propagation we published in 2015 and leads to the single heat map per analyzed prediction, and it applies a conditional masking operation. For example, let's say this one is the LRP heat map for dog, where we see that the dog's head is highlighted, so the dog's face must be important. This is my interpretation of what the model has been doing here. What CRP does is it selects a set of concepts or concept encodings in a conditioned set theta, whatever. It selects those concepts which are used by the model. This can be obtained by ranking relevant concepts in latent space, again, due to attribution information obtained with XAI, and then selectively let's pass this information through in the backpropagation step. So we can not only explain, for example, the outcome for class dog, but the outcome for class dog in the context of the use of the concept of snout, which is represented by latent filters and channels, for example. And this allows us to disentangle the different factors of the decision-making in the model per example, which has been predicted upon, and we can get an individual assessment of basically the influence of those features in input space and heat maps with that. And we see, for example, that while the dog feature is quite distributed, it pops out way more, not the dog feature, but the fur feature, it pops out way more in this heat representation in the bottom right. And if we can use this also to assess the actual influence of this, and in the end, by measuring, for example, and this measuring is possible since CRP as an extension of the LRP toolset is conservative in its relevance propagation, which means that if we sum up those relevance attribution scores for this dog heat map, we know exactly how much this feature influenced to the decision-making of dog. And we see that, for example, fur is much more important than the eye feature. However, it just doesn't pop out in this heat map as much because the comparatively lower relevance scores allocated to the eye feature is concentrated on a smaller set of pixels, and therefore the average amplitude is higher. And this is misleading us as human investigators in this case. So, and with this, CRP enables a bunch of new tools for analyzing neural network decisions. For example, we can analyze local regions of interest. For example, ask the question, where is which feature recognized by the model important? We know, for example, where's the fur located? Where is the model recognizing snout and eye features? But if we aggregate those relevance scores meaningfully between layers, we can also analyze hierarchical compositions of concept used by the model. For example, is this blue jeans feature actually depending on the recognition of the feature of the color blue, or is the blue jean feature generalizing over different other colors of trousers, for example? So in summary, CRP enables us to basically refine the where is something question when we explain decision making. For example, here we can know that there's something which has to do with lizards. There seems to be something which has to do with the vegetation background, but it does not answer the what question, basically. And for this, which we need our second method, which is relevance maximization. But before I get to that, I want to quickly highlight the field of global explainability, which is on its own concerned with answering the what question. What's the meaning of learned representations by a neural network? And most of the methods are, so there are two branches, basically. One branch is generative approaches, which tries to generate input images which stimulate maximally a latent neuron in order to get an image, for example, which tells us how does the thing usually look, which activates a latent neuron. And the problem with that is a research chain of research going on since 2009 that generated activation-based generation of synthetic input images usually drift up fast into adversarial regions. So you have something which is so abstract that it's really hard to grasp as a human what's actually going on here. And there are very many works which deal with how to constrain this generation process in order to get something interpretable for humans again. There's another branch of work, for example, this Zeiler et al. Paper from 2014, which is concerned with feature visualization. They try to visualize the extractors of features themselves in order to understand what's going on. Or network dissection is a nice paper from 2017, where they have used extensively labeled datasets with segmentation masks for objects or materials in order to measure which neuron activates for which of those known concepts. However, this requires that this data set for measuring stuff and comparing stuff is actually there. The paper from Chen et al., also from Cynthia Rodin's group from 2020, they find a quite simple but nice solution, and it's just getting samples from the training or any reference data set, basically, which maximally activate a neuron I'm interested, right? And since those are real samples from real data sets, we can assume at least that those are kind of human interpretable, at least in this image domain. However, we argue that activation maximization alone is not the answer to understanding latent representations of neural networks. And the reasoning is thus, if we think about what measuring latent activations actually does, is that we put in some data point into a network, it transforms this data point, and then it activates some neuron in latent space, right? And however, what this not does is it does not guarantee that this particular sample or this particular activation is actually useful for solving some task, because this activation measured here never arrives in the end. We instead argue that we should again use explainability scores in this term relevance, because what relevance does is basically also in the forward path computes activations for all latent layers, then it touches the output of the network, and then it's then backpropagated until we reach the neuron of interest again, which provides not a measure of stimulation of this neuron, but it provides a measure of utility of this data point for solving this task using this neuron. So which means activation is just the stimulation of this neuron without any task concept, because this neuron could effectively be dead after this layer. It could be unused because there's no follow-up connection, which is shown in the middle panel here. But if we have a high relevance score on this one, we know this neuron is actually used for solving a task, and therefore it's this data point which generates a high relevance score is actually useful in context of this task. Besides that, so the motivation is that we also observed in the past that relevance is barely correlated with activations of neurons, and which speaks for augmenting at least activation-based explanations in terms of examples with other quantities which measure something different, which in this case is relevance. And this leads as an outcome also to completely different sets of example images. And what I should have added before is why do we do this actually? We do this by for getting examples, for example, by sorting all the data points in a data set according to the activation or the relevance score for this neuron. And then we procure the strongest feedback ones, which means the 10 data points, for example, which have the strongest activation for this data point, or the ones which have the highest relevance, the relevance scores for this latent representation, under the assumption that given those are the ones with the strongest feedback, are the most representative for this encoding we're currently looking at. And if you compare, for example, what activation is doing, we get those examples. And this on the bottom one is what relevance is doing, which means activation tells us that filter A, for example, activates for white lines. And in terms of relevance, we get the information that filter A is used for recognizing written text in Asian lettering, for example. So the content is different, which is good. An illustrative example is this one, where we have this bird classification and we analyze some lower layer which picks up color values, and given the sample, we measure the maximum feedback in the channel output, and we see that the strongest feedback is here. This is green. The strongest feedback for channel 55 is somewhere here. This is kind of yellowish. But if we then compare the most representative examples in terms of activation and relevance, we see that activation procures green examples for both channels, while relevance procures green one for the channel 38 and yellow ones for channel 55. And the reasoning behind this is that after data transformation and mean centering and so on, if you look at what those channels are actually doing, the channel 38, the one on top here, which has both times green feedback, uses the green channel in order to, so if you maximize the green channel input, you maximize the channel output and also minimize basically the red channel. And also in the channel 55, which reacts to yellow color apparently, we also have a strong influence from the green channel, but also from the blue channel, which means if we have a data sample which just maximally puts input energy into the green channel, we can maximally activate both outputs, although this one is actually there or reserved for if you look at the direction for recognizing yellowish color. So in a nutshell, this means just if something activates, it doesn't mean that it's activating in the right level. So just maximum activation doesn't cut it. We need to find the data points which activate in a way which is usable for the model in its known and learned settings. Another nice feature of relevance-based selection of examples is that relevance is contextual, for example, which means we can ask a particular feature, for which data points do we get the most relevance for, but we could also ask for which data points, only looking at the output, for example, for class thimble or class limpkin, do we get the most relevance for, which means we can explain the same feature in different prediction contexts or task context again, which is not possible with activation alone. And by spotting all those examples, we can find or can look for similarities. What is the core concepts? And here we can figure out that in all those classes, this feature is used. For example, there seems to be a repeating smallish regular pattern, which might be the core of this concept. So another thing which is done regularly in literature is procuring full image sized or full input sized examples. However, if you look at those images, for example, we have computed for one filter in the network, we see that there's a lot going on. So what is the actual core concept? So the interpretation here needs to be made easier for the human. And what we can do actually is, since for example, in convolutional neural networks, a single neuron rarely sees the full input, but only a subset of the input based on its connection to the input space via a chain of filters. We can use, again, explainability information in order to find out the receptive field and just crop the relevant part, which is corresponding to what scale this one particular neuron can actually see in input space, which allows us to get one step further. So we can zoom in basically, or we can extract from this full image-sized input the valid receptive field which contains the core concept, which should ease the interpretation of what we are seeing here. Still, there's a lot of stuff going on. There's a lot of variation in the data, but what we can also do is, if we consider this latent representation as a detector for something, because the network has learned a representation to be there, and it's picking some particular information up. For example, in global XAI literature, there's the consensus that that neural networks, especially in later layers, they learn human understandable, quite abstract representations of things. For example, cups and stuff, which is not explicitly labeled, but it's meaningful to use. And if it's regularly appearing in the data, the model will learn representations for that. If you look at one of those representations, one of those filters, and we recognize this as a detector for something, we can again explain its output, which means we put something in, and then we compute attribution heat maps in input space, explaining what the model has actually used in this input crop to, or the filter has used in this input crop in order to be stimulated again. And we get a heat map in this context, which zooms further into what the model is actually using in this case. And then if we post-process it a little bit and use this filter, for example, to create a mask, we can get something like this, which allows us to see that those examples in the top row actually are there because they have this regular ring-like structure, which seems to be the learned concept for this representation we are currently investigating. So we are, again, one step further in the direction of cognitive optimization for explanations. And now if we combine what we have achieved with CRP and relevance maximization, we can build a concept atlas. This is what we call it, at least. We see it to the left, where we have for one input image, we can get a traditional heat map for comparison. But we can, for example, if you pick a layer of our interest, let's say we have something very high in the network, we can rank the channels of this particular layer according to relevance, and then procure the, for example, in this case, the top case, in this case, top 5, most relevant, most impactful channels, which have been mostly influential for the prediction of the lizard class in this particular case. We can compute CRP heat maps focusing in the input space of the given image where this concept encoded by this channel 469, for example, is focused on. And we can, with relevance maximization, provide masked samples informing us about the semantics of this feature. And then we can piece together that, for example, lizard has been recognized because there's a lot of lizardy features, which is good, but there's also a bias towards vegetation. And lizard eyes, for example, which we see are recognized here as black spots with some white bordering around, seems to be important, but also that it's sitting on a branch, for example. So context is important. We can immediately see it from this one singular explanation. And this can be summarized again in this concept atlas localization map. But the question is, given, for example, that higher neural network layers have hundreds of filters, how much information do we need to look at in order to understand what the model is doing? And the good answer in this case is actually not that much, because relevance usually tends to be power law distributed, which means we have only a few features to look at, which are, for this one particular decision, most influential. And if we try to remove the most important ones and then re-evaluate the network, we see that the output towards the lizard class, for example, this is an average over the whole ImageNet dataset, collapses about the removal of 20 features. So then we have lost 95% of the confidence of the model for predicting this class. So it's actually manageable in order to kind of fully understand what the model is doing in a semantic way, which is more ready-made for human consumption, I would say. As a complement to this top-down approach, which we have seen in the concept atlas, we can also follow a bottom-up approach where we pre-select image regions and then thereafter ask what the model has recognized, in particular in this region we're interested in. For example, the beak has been recognized based mostly on color features, and the wingspan has been mostly used for predicting due to its texture, and so on. The question is, how much time does it cost if we want to compute it? It's actually quite efficient. So what takes some time in the order of minutes? So if we have a bread and butter consumer grade GPU, the validation data set of ImageNet, which is about 50,000 samples, takes 20 minutes to fully process until we have a data bank mapping each single feature encoding in the network to a list of most representative examples with masked stuff and so on. And if you then want to compute a concept atlas for a new data point, this is just a matter of seconds, a couple of forward and backward passes through the model, and then you have your concept atlas explanation without much time consumption. So, but since the topic of this talk is actionability in XAI, the question is, what can you do with this kind of stuff? And one thing we did and we can do is demonstrated here at hand of the ISIC dataset for skin cancer detection, which has some known problems, for example, that colorful patches and also other features which we found out later are poisoning the dataset, which are highly correlated with a non-cancerous Nevis class. And we can, with our methods, find the exact representations of those filters in different layers. For example, lower layers where color features are important, higher layers where the actual patch is important, and then isolate it and investigate its actual impact, for example, for the outcome of predicting this one particular class. And if we then, for example, take some non-NV class samples, which are those melanomocytic nevus, this non-cancerous one, and we inject in latent space activations copied from samples with patches, we see that if we blend in or we increase the strength of this one channel, the output confidence for the NV class, we are operating only on this one channel, right, which has been associated with the patch encoding. We see that the confidence output for the NV class rises, and at the same time, other patch feature relevances increase as well. And on the other hand, if we find samples which have this patch and we remove it, we see that the class drops again. So we can surgically investigate the impact of human understandable features by directly identifying and finding latent encodings in a human and computer interactive way. Another nice thing is, for example, illustrated here, if we have the a prediction from ImageNet where there's the class safe or lockbox, and we compute an explanation for it, we see that there's a suspicious band in the middle, right, where relevance is concentrating. And if we then do a bottom-up analysis and ask what's actually, or what are the most important concepts or higher level feature encodings in there which impact the model decision, we see that there's a lot of features associated with writing again. We can investigate how big the input actually is by suppressing those filters and deactivating them, setting them to 0. And we see that it does not hurt the confidence of the model to detect the safe class. So there's apparently enough other features left for safe detection. But we can then, if we know that such an encoding exists, we can do a reverse search and ask, for example, which other classes or which other samples are also affected by this, by measuring for this particular encoding the relevance generated on average by other classes or by particular samples. And if we rank those classes, for example, we find that there are other classes actually actively using this filter. For example, classes Whistle, Mob, Screw, MosquitoNet, and Can Opener are using it, and they are also abusing this feature as a detector for writing in order to predict those classes because they are associated with this copyright watermark again. But there are also other classes like Puma or Spiderweb, which also make heavy use of this feature, but in a benign way. For example, they use it to recognize the whiskers or the spiderweb itself. And this might basically prompt us to say, let's remove this filter. It encodes an artifact. We don't want it to influence our prediction on Whistle. It makes our model attackable, for example. But on the other hand, if we remove it just outright, we would also hurt other classes which make valid use of it. And there might be other strategies needed in order to really fix the model in this respect. But at least we have now a, a hook to start with, and we have detailed information about the behavior or misbehavior of the model. And as an outlook, we can, which is in the paper if you're interested in, link will follow soon, we can use those methodologies to investigate filter encodings, latent feature spaces, and their detailed interaction. For example, what we found is that there are oftentimes filters in the network which behave highly similarly to one another if you measure the activation spectrum, but they have contrasting behavior in terms of relevance. For example, this cluster here has been found by behaving, if you pipe in input samples, quite similarly in terms of activations. They extract some features which are button or shingle-like, but the detail in this cluster is that it seems to be, its function seems to be differentiate between different kinds of buttons, for example, laptop and keyboard buttons, or round buttons for remote controls and so on. And this seems also be the use case of this cluster of filters as it is being used by the model. Okay, to conclude, there are also some other noteworthy mentions. For example, the tools we use, like Zenit or Julia package from Adrian Hill from TU Berlin, Quantus, a toolkit for basically quantifying the goodness of or quality of explanations in a large scale to make it reliable automatically. And finally, I want to thank the European Union for funding parts of this the presented works in this talk. Thank you for your attention. I'm quite a bit over time, but it's not unusual for me. If you want to look at the paper, follow this link. It's an archive right now. If you want to use the methods, you can use this standard CRP, repository on GitHub, and directly apply to your PyTorch models and play around with it. Now, everything else which follows is 10 pages of references, which you can look at yourself when you download the PDF. Thank you.
Dear Sebastian, many thanks for very inspiring and interesting talk. Now we have time for probably short discussion and questions from the audience. Before somebody will raise a hand, I'm analyzing the chat. So if possible, I will start from some questions I have found in the chat, if you agree. Others can be ready. So Dominic Kosman is asking about CRP method, your new method, and he's asking in the following way: where did you get the lower level concepts from? So probably the question is about how do you identify the small concepts you use in the concept relevance propagation? Is it completely automatic, or you must analyze them, interpret, etc.? Could you comment on it?
Yes, okay. 1 second, I'm screen sharing again. So teaser, when I'm moving to the slide, when you have any questions which cannot be answered here, please shoot me an email or write me on LinkedIn. We get those examples. I guess you mean those example images, right? We get them by just measuring their influence on the decision making of the model by analyzing a data set. So in a nutshell, it's, let's say you have one particular layer you're interested in and one particular feature you're interested in, one particular feature encoding. And this is what we're currently looking at. So what we do is we take the ImageNet validation set, we pipe it through the network in the forward pass, and then we explain it in the backward pass. And basically, in the backward pass, we allocate, or while we move through the network, which are relevance scores, we allocate for each image a certain amount of relevance to this particular feature we are currently looking at, this feature extractor. And this is the quantity which we use to rank those images, right? We have this ranking of 50,000 images now, and we take the 20 images which have the highest relevance scores, and then associate them in a data bank, for example, as representative to this particular feature we are looking at. I hope this answers the question. So yes, it can be fully automated.
Okay. I think I have noticed one question somewhere around about relation to using all the background knowledge. So probably I will formulate a question whether your approach could be also used with some already prepared concepts or candidates of features.
Yes, it can. So our goal with this work is actually to be free of those assumptions, right? So say we have an end-to-end learned model which has learned on its own some feature representations for which we just need to measure relevance. But this does not exclude that you can build your own network which has some reserved representations for things and features and concepts, and still explain it in this way. So in a way, CRP and relevance maximization is compatible to using hybridly semi-controlled built neural networks, if you want to speak so.
Okay.
So we have some external experiments on that, and we can actually measure, for example, if our handcrafted features are preferred or better for the neural network than end-to-end learned ones. This would be one setting.
Another question I see in the chat is from Tony Zhang. He asks, how do you evaluate how good are your methods? So I guess it's a question about the evaluation procedure, whether you will have found really a good explanation.
Yeah, it's a good question. So I've also seen in the chat that someone linked the Quantus toolbox. And I have to say that evaluating explanations is quite hard due to the lack of generally the lack of ground truth knowledge. And if we have ground truth information, it only reflects an expectation we have as humans, but it rarely really reflects what the model is actually doing or has learned to do, right? So this is kind of this chicken egg problem in explainability. If you evaluate explanations, you are co-evaluating the model itself. The Quantum's toolbox is there for basically evaluating local XAI methods, but in this context of the concept-based explanations, there is no really set way to do it. So what we're currently doing is we're running user studies with real humans, and we are asking them questions which let us infer how useful this information actually is in order to make some judgments about the model's mode of operation. And as far as I can tell right now, it's looking quite promising that this concept-based explanation is way more informative to the average user than, for example, just a heat map, because it avoids a bunch of the problems we have with single heat map explanations.
I guess it's a bit consistent with the famous paper about rigorous evaluation of explanation method by Kim and Dolores Valdez. They strongly promoted studies with humans to evaluate the quality and also taking them into account in some actions with the explanation. But yes, I see a quite similar comment or a question in the chat from Łukasz Borowiecki. What is the adoption rate of XAI methods among people who are not strong computer science specialists? So I guess he is probably asking that these methods requires quite a good experience of the user. Could you comment more generally on it?
So I cannot comment really on the adoption rate as a non-expert, because, well, this is my field and I'm very familiar with what's going on here and how to read this information. But what we found is the key is you need to train your operators in order to read this information, right? If you just provide a heat map for a prediction to some random person on the street, they would have no chance making something out of value from this bit of information, right? You need to train the people, or at least guide them in interpreting how to read this information, and then it becomes useful, right? But also depending on the data, how readable is the data itself, and so on. But to summarize, their training is required, I would say.
Yes, it is also another comment, but before reading it, I will probably also encourage audience that you can raise hand, etc. So we can also try to put you in a direct question. So somebody is asking how sensitive are these methods to adversarial attack? If your system is somehow attacked by suspicious actions.
I assume that you mean CRP and relevance maximization, right? In this particular context, yes. So we found that relevance maximization for selecting examples is quite stable, because it measures basically the utility of a feature, or the usefulness of a data point in the use of a feature for the final task of the model. So if you go to some adversarial space, there are very few examples popping in our rankings, right? Those are really good examples. Heat maps themselves, however, there are some papers from the Technical University of Berlin around Ann-Kathrin Dombrowski and Christopher Anders. They deal with this question that, for example, especially in the ReLU-activated networks, you have those many discontinuities in the activation space, basically where your gradient jumps from 0 to 1. And if you have an explainer which is bound to gradient-based representations, they can be fooled, right? You can even train models which behave in one way in terms of prediction making, but give a completely different explanation because they can exploit those degrees of freedom. And once we have, I don't know, the heat maps, I would say, are still susceptible to the same effect. But in terms of the relevance maximization based examples, we have seen an increase in stability over post-processing choices or score aggregation choices compared to activation.
Okay, thanks. Nobody is raising hands, so I see a question from Nilach Ravinair about are there research with CRP applied to other domains, I think, than images. He is asking about time series data, for instance.
Yes, we have in the archive paper, in the appendix, we have a time series example. You can apply it. So deep neural networks, basically, they process numbers, right? And the inputs you give from some domain of choice, in the end, you need to transform it into some numerical space and feed it into the network. And the methods we talked about today, they just operate on the neural network level. So which means anything which can be represented as a number is compatible, at least in theory, with CRP, relevance, maximization, and so on. And the final step you need to take is to find for those examples to give in order to communicate the semantics of the features used by the model to find suitable representations. And for time series, it would, for example, be you crop some parts of the time series, one particular neuron you're currently looking at reacts the most strongest to. So yes, there's application scenarios outside image, but images work well in talks, and therefore we usually show images.
Okay, we have quite interesting discussion with you. Again, a question nobody is interested in raising a hand and asking directly. Okay, I'm quickly looking whether we have something. Okay, Antoni Jamilkowski is asking about, is it possible to cite or to a bit more precisely define the term, the cognitive optimization? He says that there is a lot of philosophical issue which could measure its reliability. So could you comment on it?
Yes, I would actually direct you to the paper, or where is it, from Hacker et al. From 2022. But cognitive optimization basically describes how readable is the explanation to the end user, right? For example, I would not, whoops, where is it? I wouldn't regard this one as well cognitively optimized, right? Because in each case, you see, it's just the bird. The bird is important. This is not a cognitively well-optimized explanation because we don't get any more information.
Okay. I guess we have a volunteer to ask a question because I see raised hands. So Freya, please switch on your microphone and ask a question directly.
Hi, good evening. Can everyone hear me all right?
Yes. Yes.
Perfect. All right. Thank you for the very interesting talk. So I had a question about how we can be sure that the XAI method, like the explanation of it, does actually correspond to the actual model behavior. Because the way I like to see it is like if the XAI method is a translator and the model talks in like a foreign language, how can I then check if this translation is correct? Because, well, of course, I don't know the model or the language of this model, and maybe there might even not be an exact translation possible.
Yeah, and this is quite difficult, and I think this is a problem which is not fully solved, to no extent solved, actually. But this is something we have built the Quantus toolbox for. The Quantus toolbox is collecting over 30 currently different XAI quantification methods, which are measuring explainability quality in different aspects. For example, how faithfulness is the explanation to the model, or how well does the explanation correspond to some expected ground truth, bounding box, and so on. But I personally think that the field of quantization or quality measurement of XAI is totally far from done, right? So this is difficult because, as I said earlier, usually if you want to evaluate the goodness of an explanation, you are also at the same time evaluating the impacts the model has itself on this whole process.
Okay, thanks for the question. So because we are slowly at the end of the time limit, so I guess there is no more raised hand. So Ioannis, I think we will slowly close today's session. So dear Sebastian, many thanks for your very interesting talk. And I think that if somebody has still some questions, you will agree that she or he will send you email with more precise question and you will handle them. Yes? Okay, so Once again, thanks very much to our presenter for excellent talk, and we are closing today AIDA Excellence lecture.
Thank you very much, Sebastian. Jerzy. One question, Sebastian, you grant us right to record the lecture. Can we post both the lecture and the PDF you send us?
Yes, you can, please.
Okay, good. So thank you very much. And please do consider to become an AIDA senior or curator. Okay.
All right. Thanks for having me. It was quite fun. Any unanswered questions, shoot me an email. I'll try to answer them all.
Okay, once
Thank you
again, thanks.
Bye.
Bye-bye.
Bye. And thanks everybody for participating. It was great that 170 something in one peak was with us.
By the way, before we leave, let me announce this thing to the rest of the people. In AIDA, we try to introduce this notion of AIDA curators. This means people that know an area well. They are young and energetic. For example, postdocs, assistant professors that have a little bit more time than we older people, that they want to upload useful educational material in AIDA, and they would be willing to curate it. So if there is anybody that wants to become an AIDA curator, just send me a message. Okay, thank you again. Bye.